Welcome to the course on FPGA based signal processing systems. This is lecture 5, introducing Verilog. In the Verilog FPGA module, the FPGA architecture, especially, that we have seen that there is a logic block arranged in a matrix pattern, and there are switches all over, and there were interconnects as well. So this is the FPGA block diagram we had seen, and these logic blocks have been chosen for design and the interconnects also, the switches even in the programming. So when we come to the Verilog module, so how this Verilog is coded, actually the hardware description language, here straight away we are looking at the Verilog, not the VHDL in this course. So Verilog, which has the declarations part, the module, Verilog module, each has a declaration and statements. So the declaration and statements consist of the module. So Verilog module, we can say, consists of declaration and statements, so which is called the module. So how this each module is going to be coded, and what are all the declarations it can have, and what are the statements, possible statements it can have in a module. So when you say a program, Verilog program, it is called a module, and that module contains the declaration and statements. So now if we come to the modules, each module, you can have multiple modules, and the modules can instantiate other modules hierarchically. So for example, if we have the one module declaration and statements, and it is called module A. We have module B, that is another lower level module, also module C, which has declaration and statements, module D that has the declaration and statements. We have the module E, which is next lower level module, and module F, declaration and statements, that is also as another module in the next hierarchy. So we have the module A is the first top level, and the next in the hierarchy, next one, that is module B, C and D, also the module E and module F. So the instantiation, meaning that one module can call the other module inside the statements. That is if we have the module B is called by the module A through the statements, and module C also called by the module A. Here you can see multiple times you can call this module C. This is called instantiation. So instantiating a module B in the module A, or in module C in module A 2 times. The module D, which the arrow mark shows, that module D can be called by the module A in the statements. That is called here usually the calling functions in other languages. This is in the Verilog, we say that it's instantiation. So module B, C and D are instantiated in module A, and module C is instantiated twice. You can see the next lower level modules, that is module E is instantiated in module C, and E is also instantiated in module D. Also module F is instantiated in module C, and F is also called in D. So it is instantiated in D multiple times in D. So this is possible. So this is called the instantiating the module hierarchically in the other module. So it can be multiple times used by one module, the top level module. So this is about the instantiating one module in the other module. So Verilog module can instantiate other modules, and higher level module may use the lower level module multiple times, and top level module may use the same lower level one, it can use as well. Okay, so now what is we'll see the syntax of the Verilog. So how the single line comments are used in the Verilog. It begins with a double slash. So the single line comment begins with a double slash, and end at the end of the line, whatever the line you have used. So for a single line, you just start with a double slash, that is a single line comment, and the multi-line long comments, so multiple lines, should be started with a slash and asterisk, and end where do you want to end it, with the asterisk and slash. So this is illegal. So when you have started, and it should end, okay, so this should come in the where you want to end the comment. So asterisk and slash. Okay, this is an illegal comment, for example. So there are keywords which are also called reserved words, okay, in the Verilog. One is module. Module is a keyword, input is keyword, output is keyword, assign is a keyword, and end module is a keyword. So we are going to look at this small program that which has these keywords. Okay, so every module, so how a Verilog module should be written. So the Verilog code. So module, first you have this a keyword and end module. Every module should have an end module. So the Verilog module is a keyword and end module is a keyword, and then we will write the module name. That is, this is an AND gate program. So AND underscore gate, this is a module name which is of your choice. Also the port names, and these are ports called X, Y and Z. Every port name should be separated by a comma, and these port names should be within the bracket. Also every line of the code should end with semicolon. Okay. So this module name and port names, this within the bracket X, Y, Z. So after that we have this input, the declarations. So here in this AND gate, X and Y are inputs. Okay. So X input is a keyword, X comma Y. So the comma separated, the signals are the identifiers. These X and Y are called identifiers. So the port names should be separated by comma, and that every line of the code should be ending with a semicolon. So these are X and Y are inputs. So output declaration, which is Z, the output is Z. So if we take this AND gate in our example, that is X, this is X and this is Y and Z, simply the AND gate and digital gate. So X is the input, 1-bit input. Anyway, X and Y default here. If you just write port names X and Y, and that is meaning of the default 1-bit. X, Y and the Z is also 1-bit. So the declaration. So when we see the module which has the declarations, so these are the declarations: input declaration, output declaration. And then comes the statement. What is that? Assign Z, the output, equal to X and Y semicolon. So this is an assign statement. The assign is also a keyword here, where this statements, these are the statements in the module. So these are the declarations in the module. So we have the declaration and statements. So the statements will be different for different modeling. It can be of the structural modeling, data flow modeling, or the behavioral model. So depends on that. This statements would vary. So it's initially to start with, given this assign Z, the Z is simply ANDing X and Y. So that's the example we have given. So this is a simple program to start with, an AND gate program, which has, as we said, the keywords are given in different colors or reserved words. Also have the module name which is of your choice, and X and Y. X, Y and Z. X and Y are inputs and Z is the output. This can be written for any logic gates. It can be the assign Z, and we are going to see the operators, logical operators in this, and how to use them. This is an AND operation. Okay. So now coming to the identifiers, use of identifiers. It begins with a letter, underscore, okay. So and can contain even the digits, okay, and you can $sign, all of them. These module name we had used. No, those module name can be, it can have underscore, $sign, and then letters, digits, and so on. These are identifiers. And AND gate, in that previous example, AND gate is an identifier. X, Y and Z are identifiers. Also the Verilog is case sensitive for both keywords, that is, keywords are lowercase only, and identifiers also. This is case sensitive, meaning that capital X and capital Y, and then small x and small y, capital X, small y, small x, capital Y are all different. So these identifiers these are case sensitive. So when there are blank spaces, which is /b, and we can say the tabs use a /t, and the new line can be /n, which can comprise the white space as well. So these can be used in your code: blank space, tab, and then new lines. So the syntax of the Verilog module: declaration. So what are the declaration parts can contain? At least I have listed some here. So every module should have an end module, all the module name. The next one is this module name, also the port names, next X, Y, Z, that just can refer it to the previous example: port name X, Y, Z, and semicolon. So the input declaration, input and its declaration, what are the port names, and then output declaration. So every port name what is given within the bracket here needs to be declared, either it is input or output. That is essential. and in-out declaration. So, the signals can be input, or it can be an output, or it can be in-out. That means the output of one module can be the particular signal can be used as an input to the other module as well. So, then it is in-out declarations, and the net declaration, whether it is a register or it is a wire, we are going to see them in detail. These are coming under the declarations. So, we need, and then variable declaration. What are the variables you use it? Parameter declaration, another function declaration, task declarations. Okay, so these all contains the declaration part. In a module we have the declaration. So these are the declarations, and then comes the statements which are concurrent. So the concurrency, we are going to see them in the examples, which is unique to the Verilog. And then we see in the previous program there is a keyword module and identifier, AND gate X, Y, Z are identifiers, and then list of identifiers as well we have given, and the declarations we had, also the keyword, which is N module. So this is the list of the program which we had looked into. So the input and output ports are the signals through which that the module can communicate with the other modules. So that it can take the input from the other modules, and it can give the output to the other modules as well. So this way this can be communicated. If we take these input output declarations especially, so the input, as I said, it should be listed, all the inputs should be listed with a comma separated one. So each input port is an identifier which should be closed with a semicolon in each line, and then output is also comma separated identifier. Okay, and then in-out can also, that means you need not write X input X input Y. So 2 times you need not be in writing it again in the declaration. In the you can merge those declarations, all inputs in one line with the comma separated identifiers. Similarly, the outputs also can be listed as a comma separated identifiers, in-out declaration also. And in this case, the previous ones, inputs and outputs are in-outs are single bit vectors. So the inputs can be multi-bit vector as well. So that is the 8-bit vector. So in that case, there should be a square bracket. The input should be declared as the square bracket having the LSB and MSB. So here 0, suppose 8 bits, it is going to be 0 to 7 this way. It can be written. It can be written in the other way as well. The output also can be LSB and MSB, or it can be 0 as well as 7. So we can write LSB colon MSB also, that is even acceptable in the Verilog. So 0, 7 or 7 colon 0. Yeah. So all identifiers, suppose you are writing X comma Y as 7 0, meaning X is of 8 bit and Y is also of 8 bits. So the inputs all of multi-bit, this is the multi-bit declaration, the port, the identifiers are multi-bits here. Also the in-out declaration, so input multi-bit and output multi-bit, and then in-out declarations should be in this way. This is the syntax for it, and each port name must have this input and output in-out declaration. So every as I said, within the bracket, what is the port name list of port names or list of identifiers given over there should be declared in the declaration section. And the keywords should be followed by this, the keyword input, output, in-out is followed by a comma separated list of identifiers. So I've said, and its corresponding type also. So the keyword specifies the signal direction. So if it is declared as input, so the signal is an input to the module, and if the signal is an output, then it is coming out of the module as an output, as in the case Z in our case of AND gate. Also the reg declaration is needed to read the signal in other modules. So reg and net and wire, all of them we would be discussing in the coming lectures. Also the in-out declarations, the module input or an output, or it can be considered, it can be used as an input or an output. So the signal can be multi-bit or a vector also. It can have the multiple bits. It's not necessarily a single bit. So the range of bits, as I said, is 8 bits or 16 bits. Suppose it is 0, colon and 15. So that is for the 16-bit vector multi-bit we can specify, the signal can be specified in this way. So now the range can be ascending or descending, as I said that this can be 15 or 0 to 15, this anyway. So the operators, let us see in especially the in Verilog, if you say A is equal to tilde B semicolon. So A and B are identifiers. Here A is A here is the signal, B is the another signal, and the tilde is the unary operator. So tilde is negate, is the unary operator, B is the operand, B on which the tilde is acting on and saved in A or stored in A. So this is tilde or unary operator, and there is a binary operator and A equal to B and C. Okay, so this is, there is a difference between the logical and the bitwise and. Okay, so the B and C is a, we have this AND logic. Also, this is called the binary operator. We are going to see the logical and bitwise AND operations. These are B and C are operands over here. So this is binary. So binary operator, it is acting on the two signals B and C. And then the ternary operator, which is very unique to this Verilog, you have this three, this is called which has this question mark and colon. So A equal to B question mark C colon D. So B, C, D are the operators. So here operands B, C and D, and if this is checking the logic here, suppose B is true, C will be assigned to A. If B is not true, D will be assigned to A. So that's the ternary operation here, which is very important. So if B is true, assign C equal to A. If B is not true or false, and assign D to A. So this can be written in single line. So B question mark and then C colon D. So that's a ternary operator. B, C, D are the operands here. So we have the unary operator and then binary operator and then ternary operator in the Verilog. So number specifications. So we look at the number specification, the sized numbers. So how the numbers are specified in the declaration. So size, apostrophe, that is essential, and the base format and what is a number. Okay. So let's look at the examples now. B, that is equal to 4. 4 represents the size of the number, that is the bit size of the number, which is 4 bits, and apostrophe, which is given over here, and the base format, whether it is binary or decimal or octal or the hexadecimal. So the base format is given in B, and the number itself is given, that is 111 is the 4-bit binary number. So it's when you specify 4 apostrophe B 111, meaning this is a 4-bit binary number, which is 111, the number 111 4. This is the 4-bit binary number. So similarly, if you have this is an example for the 12-bit number apostrophe, it's a H is the base format, it's a hexadecimal, and ABC is the number. Okay, so ABC, the 4-bit number, 4-bit each, ABC, a 4-bit combines it, giving the 12-bit here, 12-bit hexadecimal number ABC. So the representation gives the numbers needs to be, these are sized numbers. So it is specified, this is 12-bit or 4-bit, this has the size, bit size, and then 16-bit here, and the specific this is 16-bit number of decimal 255, 255. Okay, so this is a decimal number with the 16 bits is represented like this. And then unsized numbers, for example, here 2, 3, 4, 5, 6. If you write like this, it doesn't understand, but see that the default is 12-bit decimal number. Okay, sorry, 32-bit here. If you take it as instead of 30 instead of the bit size, there is no bit size mentioned here, so it's a 32-bit decimal number by default if you don't specify the size. Okay. Then again this unsized ones, there is no bit size specified, apostrophe is given, H is given, that is saying that it's a hexadecimal number, and C and 3 are the number, C3 is a number. So it's a hexadecimal number, the base format is specified, whereas in this case there is no base format specified, so it takes this as a decimal number by default. In this case it is specified, the base format is specified, so it's an hexadecimal number, but the size is not specified, so that is considered to be 32-bit. So 32-bit hexadecimal number. And then here again there is no base size specified, but base format is specified, which is octal 21. 21 number 21 is the number, and octal there is no size specified, so it is going to be the 32-bit octal number. So whatever missing, whether the data format, the size or the format is missing, then it is going to be assigning that 32-bit default as decimal. These are unsized numbers. And if you say x or z values, so 12-bit for example hexadecimal number with 13x. Okay, so here is a 12-bit number. Yes, size is specified, and what is the base format? H hexadecimal, fine. And then 4 least significant bits. So 1, 3 are known. If it is 12-bit, 1 for it takes 4 bits, and then 3 again takes 4 bits to represent in binary. So that, and then x is unknown. So the x is considering that another last 4 significant digits are unknown. So x, if you write x, it is considered to be unknown. So for 12-bit for hexadecimal 13x. So 1, 3 and x it will be, if you write it in the binary, it will be that 0001 and 0011 and then x will be this number. And then a 6-bit hexadecimal x. So the x is now, the x is repeated for then 6 bits. Okay, so it's a 6-bit hexadecimal number. X is unknown here. And 32-bit z. So the z is here the high impedance state, actually high impedance number. So which we call it in the tri-state buffers. We use the other state of this, that is the high impedance state. If you specify z, that is going to be. So here the 32-bit high impedance state or high impedance number is to be considered. Z. So x and z has some meaning in this Verilog. So negative numbers, how do we represent the negative numbers? So negative numbers minus at the front, very front, you have to give this negative 6 bits apostrophe, d is the decimal number and 3 is the number which is the number to be specified. So how these negative numbers are stored? Negative number representation is this. So when you define in the declaration section, the negative number is going to be x is equal to minus 6 apostrophe d3, then it is stored as a 2's complement of the 3. Okay, so the 0011 and then convert 1100 and add 1 to it. So 2's complement of this will be stored in this place as a negative when you just specify negative number. So the negative sign should be at the front. So minus 6 apostrophe SD3. Okay, so this is a signed integer or the signed decimal here, signed integer. So SD will take this signed integer math for performing. So it's 3. So it is taking the signed numbers. Okay, so signed integers can be represented like with SD. So not with D only, decimal. The SD represents the signed integer. So it can take the positive and negative values as well. So the negative number is specified with signed SD3 here. Also 4-bit D minus 2, see the minus 2 is appearing after the base format. So that is illegal. So the Verilog cannot recognize this. So you should not use the minus sign in between any of this base format or size or anywhere. So it should be before the specification of the size. And the strings, yes, this should be represented with double quote. So FPGA based signal processing system is a string here, and A/B is a string here within the quote. Whatever you write is going to be a string. This is another data type. So here the again underscores and question marks, does it have any meaning? So to represent a binary number, suppose we will take an example of this underscore. What is the meaning of this underscores here? So 12-bit number which has binary and 4 bits 111 underscore 000 underscore 1010. So that it is giving the underscore. This underscore is used to represent, give the clarity to the representation. So here 111 4 bits and then underscore 000 underscore 1010, so it's acceptable in the specification. So it's a 12-bit number, a binary number. The base format is B and it has 12 bits, 4 bits after this underscore, 4 bits of the underscores, and so it is better readability, it gives the better readability in this case. 4-bit 101 question mark. So that is binary 1 0. What about this last 2 digits, that is done in this 4-bit binary number? So it is equivalent to take the question mark is understood as Z. Okay, so it's a high impedance state. It is not unknown, it is high impedance state. So identifiers and keywords like this reg value, that is reg is a keyword here, register value is a register. Okay, so here given, so it's not actual physically what we call as a register, so there is a different meaning in the reg value. So reg is a keyword and value is an identifier here. If you say that this is going to be register, and input clock is identifier and that is an input. Okay, input is a keyword. And we have this logic system. So in the logic system, so Verilog uses 4-valued logic system. So here that you have this 1-bit signal can take on one of only 4 possible values. Like we take 0, that's a logical 0, false. 1, logic 1 or true. And then X is an unknown logic value. Z or Z, high impedance state, or the 3-state in the 3-state logic we use that as a high impedance number. That's, it has a 4-value logic system. So the data types what we have is, so the value level in the hardware is how it is considered. The 0 is logic 0, which is going to be the false condition, and 1 is logic 1 and it's a true condition. X is unknown logic value and Z is high impedance or floating state. In the hardware circuits it is considered to be unknown and here it is floating state. So the arithmetic or shift operators in the Verilog. We take the operator and its operation. What is the addition operation? Represented by a plus sign, and the subtraction operation is a minus sign. How do we add and subtract the logic? And then the multiplication is a asterisk, also the division is a slash. Okay, and the percentage symbol or the modulus which gives the remainder is a percentage, and shift left is left shift is less than symbol, and shift right is greater than 2 times. So this is the operator, left shift and right shift. So these are the operations, the arithmetic operations as well as the shift operators. So very much useful, we will be using them, all of them in the Verilog. So these are the operators of in the Verilog. So shift register, suppose if it is left shift or right shift, I think it is understandable. So if we have this 8-bit, suppose 8-bit, now you can see the example, an apostrophe binary number which has 11010011, and it is left shift by 3 times. 3, if you write this, just left shift by 3 times. Okay, so you'll be losing these bits. Okay, so these bits in the one shift you'll be losing this bit, and other you will be losing the other left shift, it will be 1 and 1. So you'll get this 1 0 0 1 1 and 3 zeros are added when you have the left shift. Okay, so this is the shifting left. So similarly the shifting right would be 0 1 1 would go off, and then you have 0 0 0 1 1 1 0 0 1 0 will be the right shift. If you have this symbol right shift 3, so it's a left shift and right shift operations in Verilog. So the bitwise Boolean operations, let's see that there is the AND, as we said the first example we took AND, so it's a bitwise Boolean operator. So discussing here to differentiate between this bitwise Boolean operator and the logical operators. So OR is a line of given as an operator, and exclusive OR is a cap symbol, and then exclusive NOR is a cap with tilde or tilde cap, both are acceptable. Cap tilde or tilde cap, anything can be used. For the tilde can be before or after the cap, or exclusive NOR, and exclusive OR is cap, not is tilde. Okay. So these operators are bitwise. So, logical operators. So, we see the logical operator, the operation and these operators are listed. Logical AND. So, double AND. So, when we say A and this is a logical AND, not a bitwise AND. So, the two ampersand symbol of 2 appended, this is a logical AND. Similarly, logical OR has 2 lines of OR. Logical NOT is exclamatory symbol here. And the logical equality, it's going to be double equal to signature, that is double equal to sign, and then the logical inequality is having the exclamatory and equal to sign. These are all logical, and greater than has this greater than symbol. Also, greater than or equal to will have this greater than symbol and then equal to, less than and less than or equal to. Okay. So, less than or equal to, these are logical operators of the Verilog. So, there is a bitwise operator and the logical operator. There is a difference between these two. So, if we say 1 bit 1, that is 1 apostrophe binary 1, that means it is true. In the logical, it is considered to be true. And if we say 1 apostrophe b 0 is false. Okay, so 1 and this is false. When we say 4 bit binary 0 1 0 0, this is true because out of 4 bits 1 is 1. Okay, 1 bit is 1. So, that means it is considered to be true. So, any one of the in logical operation, so any one of the bit is true, then the whole bit, all 4, that 4 bit is considered to be true. Okay. And if 4 bit binary 1 1 1, this is also true. So, there is no difference between this 0 1 0 0 1 1 1 or 4 bit in case of logical operations. Okay. So, that is why it is preferable to do the bitwise. Okay. So, but 4 bit 0 0 0 is false. Okay. So, all the bits are 0, then it is considered to be false. So, now we can see that 4 bit 0 1 0 0 and 4 bit 1 0 1 1 is true and all. So, we will see that this is 0 1 0 0 and 1 0 1 1. Okay. So, in this case, we do this, this is true and this is also true. Okay. So, we have this, the output is true. Okay. So, but in case of bitwise, so AND operation, you will have 0 0 and 0 and 0. So, that becomes false in the case of the bitwise AND, every bit is 0 0 0. So, bitwise AND is different from the logical AND. So, in logical AND, this is considered to be true and this is considered to be true. So, the output is true. So, the bitwise will be 0 0 0. So, it is false. Okay. So, logical operators are preferred in conditional operations, not in the case of in case of this, wherever the conditional operations are if else record, if this condition, if this is true, that 8 bit is true, then the A should be assigned B or A should be assigned C. So, this kind of operations, the logical operations are preferred in that case. Thank you.